So, hello everyone. Thank you for joining us for this afternoon session of SAM. So there are 5 events running in parallel. You are here, so it's a very good choice. If you think in terms of statistics, you mentioned this morning that, Peter, we have 20% acceptance for this particular event with respect to all the other who are organized in parallel. So it's great. So the first talk this afternoon is Sorour from University of York, and she will speak about memory efficient validation of large XMI models. So please.
Thank you very much. Hi, I'm Sorour from University of York. I'm a PhD student, and today I want to talk about the validation of large XMI models and present our approach that how we can do it efficiently. So I'm going to start with problem statement, and then with a motivating example, I try to go into more details about the challenges. Then I present our approach and go through it step by step, and then mention that how we evaluate our approach, and at the end, conclusion and future work. Of course, there will be some time for questions, so I'll be happy to get feedback and answer your questions. As you know, in MD, models are the main artifact, and they are considered as the input of programs called model management programs. This program manipulates the model. They can transfer the model or validate the model or marry them. In this work, we are focusing on validation program, which means that the program that consists of some constraints, and they want to check that if the model satisfies this constraint or not. So in this scenario, when there is a model as input and a program for validating a model, the challenges that we have faced is scalability. In current technique and tools like EMF, Eclipse Modeling Framework, when the size of model increases, the memory consumption and execution time will be increased as well, which is not very preferable. It's not very preferable. So actually, we have 2 kinds of models: the models that are saved in a file, we call them as file-based model, like the XMI, or the models that are saved in a database, repository-based model. In this talk, I'm talking about file-based models. So the scenario is we have a large XMI models, which is going to be validated by a program, and the execution engine which executes the program and validates the model. As I mentioned, in EMF, there is a scalability issue, but why is the case? The point is, in EMF, the default parser, which loads the XMI file, it loads whole model into memory and then executes the program, which is not efficient because sometimes the program doesn't need all information of model. Maybe it's validating just one class. So it doesn't make sense to load whole model into memory and then execute the program. The memory is occupying with the information that are not necessary for executing the program. So we are wasting memory and loading time because we are spending some time on loading unnecessary information for executing program, right? So our idea here is that by providing 2 features, partial loading and partitioning, we can have better performance in validating the models. Partial loading means if we can have in advance knowledge about the program, that which part of models are going to be used and which part of model are necessary for executing the program, and just load that part of model, then it's efficient in terms of memory. And plus, instead of keeping all information in the whole execution and then finish the execution, if we can understand that, okay, this part of program needs this information, so execute the program till that point. But from this point, this information are not going to be referenced by the program anymore, so dispose them. Then we have more space available in the memory for executing the program, right? So let's see the example, then maybe it's more clear. Consider that we have a meta model. It's a component language. There are components that have name. These components have some ports. Ports have name and type, and these ports are connected by a connector. If these ports are the source of connector, they consider as an out port, and if they are target, they are import of the component, right? And there is an XMI model which confirms to this meta model. Here we have 3 constraints. We want to check if the model satisfy these constraints or not. Here I'm writing 3 constraints in EVL, epsilon validation language. We can use like any language, but in this work, we use an epsilon because the main point is epsilon is easily extendable. Like if you implement one feature for one language of epsilon, for example, EVL or validation, then it's easily extendable to other languages, like for other tasks, like transformation. So we use epsilon in this work as a programming language, programming framework, and EVL as a validation language. In the first constraint, there is a component, and sorry, I cannot. So there is a component, there is a constraint which check that if the name of components is starting with the uppercase letter, which is like a valid. The second one is checking that all components has a unique name, and the third one is checking that the source, the type of the source port of connector is exactly same as the target of the connector, right? So if you look at details here, for running the first constraint, we just need the component and the name of component. We don't need other parts of the model for executing the first constraint. For the second one as well, we just need the name of component for executing the second constraint. And for the third one, we need the connector with the source reference and the type attribute of that port and the target and the type attribute of target port. So as you can see, there are some information in model like incoming reference, name of port that are not necessary for executing this constraint, right? So there is no point of loading them into memory and occupying memory with this information. So this is the overview of our approach. If we consider the EVL program as input, and then there is original meta model. Original meta model is a meta model that the input of EVL program confirmed to. Then we can use a static analyzer to analyze the program and then understand that which part of model are going to be used by the program and then generate effective meta model. Effective meta model is a subset of original meta model, but the difference is the effective meta model just contains information about the program, like which part of model are necessary for the program. So it's kind of subset of original meta model, right? So using this information in the execution engine, we use a partial parser. Partial parser, instead of using the whole model, like loading whole model into memory, it uses this information and just load the information that are necessary for the program. And then in partitioning handler, we add this feature to execution engine to dispose them information when they are not needed anymore, and then execute the program using this information. I will go through this approach step by step. Then, okay, here is the same example. As I mentioned, a static analyzer analyze the program, go through the ASD of the program, abstract syntax tree, and then resolve the type and say, okay, we need a model elements component with the name attribute. So it's added to effective meta model. As you can see, in effective meta model, it's saying that we need component with the name attribute, or we need the connector, we need the output, but the other information like name of ports, you cannot see in effective meta model. If you're interested to know that what is this algorithm for extracting this from the ASD, please have a look at the paper or the essay that I published in SLE last year, because going to detail is detailed and the time consuming. So we extract effective meta model from the original meta model using the static analyzer, and now we know that which part of model are necessary for executing the program. We use partial parser. Partial parser was developed by Jahanbin in 2016. He developed a partial parser which look at the effective meta model and load the model based on the effective meta model, right? So it's skip the tag of XMI that are not presented in effective meta model and just load the model partially in the memory and then execute the program. Based on the result that he published, you can see that in the red lines, the first one is reporting the memory, and the other one execution time in default parser of EMF. So you can see it doesn't matter that 30%, 20%, 40%, 60%, or 100% of model is going to be. It's always same because whole model is going to be loaded. But the blue line shows the partial parser. that when you use the more part of model, like 100% of model, it's more. But when you use just 20% of model, because you are loading less information, the time and memory are less. Of course, when it's 100% because of the overhead of calculating effective meta model and this stuff, it's little more. So maybe when you know that you are going to use 100% of model in a program, it's not a good idea to go for partial. It doesn't make sense to go for partial first. But in other ways, it's better. Okay, so using partial parser is good because we are just using the necessary information. We are just loading necessary information. But what if even the memory doesn't have enough space even for the necessary parts, right? So we have million of elements, we need all of them, but memory doesn't have capacity for keeping them. Or another scenario, when there is a distributed system, like there are some machines, we distribute the validation constraint in all machines. Machine one is assigned to validate 1 and 2 constraint 1 and constraint 2, and machine 2 need to validate constraint 3, right? Does it make sense that machine 1 load the information that are necessary for executing the constraint 3? No, because machine 1 is in charge of running the constraint 1 and 2. So maybe the better idea is, instead of extracting effective meta model for whole program and say, okay, this whole program need this information, load them and execute the program, we interact with memory during the execution. So what we think is, if we extract effective meta model for the first constraint, then execute the constraint, unload the information. Again, for the second constraint, load the information, execute the constraint, and unload. It would be more efficient because then we have more memory available for running the constraint. Back to motivating example. For the first constraint, we need the components and name attribute. So let's load it, execute, unload. Second one, we need component name, load it, execute, dispose from the memory. And again, load, execute, and dispose, right? So maybe you have noticed as well that what's the point of unloading the information? We are unloading the components with the name attribute, and again, we are loading them again. So it's wasting time. We are disposing the memory that we need for the next constraint, and then load them again. So it's wasting time. So maybe it's better to group the constraints, right? Instead of extracting effective meta model for each constraint, we say, okay, this is the effective meta model for the first one, this is the effective meta model for the second one, and this is the third one. Now, okay, when I compare the effective meta model, they are same. It means that they are using the same information. So if they are using the same information, if the effective meta model of 2 constraints are same, I keep them in one group and tell the execution engine that load this information, execute this group, and then dispose them. In this way, instead of loading information twice, we just load it once and then execute as much as we can, like 2 constraints that are using the same. And then we load them, and for the third one, you can see that we don't need component and name anymore. So here it makes sense to dispose it and again load the information. Okay, so we can have this rule that if we have 2 constraints that they are having the same, they need same information, put them in one group. Another thing that makes sense is that when there is a constraint 1, for example, that use import class, name attribute, type, and incoming reference, and there is a constraint 2 that use import, name, type, but it doesn't need incoming. So in other words, constraint 2 need a subset of information that is needed for constraint 1. Again, makes sense to group them, right? So if they have they need the same information, or if one of them needs information that is subset of the information the other one needs, grouping makes sense. But it's not always this much straightforward. There is another state that can happen, option that can happen, that there is an overlap between the information that two constraints need, right? So, for example, constraint 1 needs import and name, constraint 2 needs import and name, but that one needs another attribute and this one needs another attribute. So what we can do in this situation, because there is a trade-off. If we say, okay, I don't care that constraint 2 need a constraint 2 need the same information that somehow I load for constraint 1, execute the constraint 1, unload it, and I'm fine with wasting this much time for loading another information because I can keep memory free, right? But the other person can come say, no, I prefer to occupy memory with the additional attribute because for constraint 1, we don't need name type. But okay, I'm fine. I want to load this attribute and execute the constraint 1, execute the constraint 2, and then dispose all information together. So this is completely depends on the model, because if we have millions of elements and the type attribute is an attribute that needs a lot of space in the memory, then maybe it's not a wise decision to load another attribute for constraint 1, because if it cannot allocate a space to attribute type, it will be failed. So of course, maybe we say, okay, I need this to be validated, so I'm fine to increase the execution time, but at the end I have the result. But maybe if I say, no, I want to save time, I want to load this and then it's crashed, then what's the point, right? So we need some idea about the model. We need detail about the model to know that what is the best in this trade-off. And unfortunately, because our approach is using static analysis, and static analysis is happening in a compile time using the meta model, we have no idea about the model. We don't know that which one is the best, grouping or not grouping. So we provide a notation in EVL and tell user that, okay, these two cases are straightforward. If they are saying that if two constraints are using the same information, if one of them is subset of another, we know that it's efficient to group. So we group for you. But as a user that have knowledge about the model, if you think it's better to group in another way, go ahead and use this notation. For evaluation, what we did is that we implement 10 constraints using the same meta model. And then we consider 3 modes. First mode is that we extract effective meta model for each constraint and keep loading and loading for each one. The second one, we use the algorithm, with the algorithm that we presented in the paper that, okay, we just combine the one that are subset or they have the same information. So we group these 2 and 2 together. And then we ask a user that, what do you think? User decide to group this one as well, like this one that have overlap. That based on algorithm, we didn't put them in the same group, but user did. And then we compare the results. As you can see, the blue line, which shows the group of one constraint, take more time because of loading and unloading parts. But in mode 2, when we group the constraints, it's taking less time. And then for the gray one, the user is slightly less because of, again, the other group that's made and the saving time. And if you want to see that how it's justified, these 3 constraints, unique name, component disconnected, and valid name, they are separate, right? So, and it takes 30 seconds for loading the first information for the first constraint, 17 seconds for loading information for the is connected constraint, and 14 seconds for the last one. And execution 10, 58, and 7, right? But when we group them, because the component is connected is a subset, and 2 other is a parent, like it's the main one, superset, and 2 others are the subset. So the loading time increased just to 17, which is for the component is connected. Because using this information, we can execute 2 other constraints. But the execution time stays same. Like if you sum up this, it will be 73, because we didn't do anything for execution. We just saving some time for loading. So in this presentation, I talk about the approach for grouping the constraints, and we think that it can save some time in loading and non-loading. The result shows that there is it can reduce the loading time because of using the partial, and memory, as I show, because of the loading, the partial parser, and execution time because of grouping. We are thinking that maybe we can support user written more, like have an analyzer maybe for models that goes to XMI and see the tag and say, okay, I think roughly like 1 million elements of this is there. So if you want to load this attribute more, like extra attribute, it takes this much memory. So now you can decide, right? But you know, measuring memory is not very easy, so it's little challenge. And the last thing that we are thinking about as a future work is explaining that setting, distributed setting, that when we have machines and then we distribute the constraint between machines. So now just ask them. Right now it's the case that right now each machine have a copy of the program and have a copy of model, and then they run the part of program that is assigned to that machine. But maybe considering this this approach, each machine just can have a part of program that wants to run and just the part of model that is necessary for that part, not loading. Thank you very much for your attention. Please, if you have any question, feel free to ask. And these are my email address. The code is available in GitHub and the LinkedIn profile. Yeah, please stay connected and let me know what you think. Thank you.